Okay, so I wanted to have a look at some linear relations problems. This is from the Year 8 and Year 9 Victorian curriculum, but I'm sure it covers lots of ground across the mathematics curriculum generally. So I wanted to just tackle it with a problem. So let's have a look. Duncan is an apiarist and collects 3 samples of honeycomb from a particular hive and displays them as shown below. Sample 1, sample 2, and sample 3 are shown there. He'd like to know more about the following relationships: how the sample number is related to the number of cells, how the number of cells is related to the number of edges, and how the sample number is related to the number of edges. So there's a bit of terminology we need to get our heads around. So each one of these hexagons is what's called a cell. Okay, you can guess that each one of the edges is called an edge, each one of the lines is called an edge, and the whole thing is called a sample. So we can see that this part here is called this whole thing here is called sample 1. Okay, so just a bit of terminology we need to wrap our heads around. Okay, one way to approach this problem to work out the relationship between some of these variables is just pattern recognition. So let's have a look if we can see if we can do that. So for sample 1, let's work out the number of cells. So we've got 1, 2, 3, 4, 5, 6. We've got 6 cells. Let's count for sample 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Alright, and this is why I've called it pattern recognition, because you can probably see, if you haven't already seen it already, if I just do an outline around this sample, okay, you can probably see that it just repeats. So if I do a line around there, you can probably see that the sample just repeats itself over here. So that's helpful. It helps us count, right? Because we know for sample 2, well, if sample 1 had 6, sample 2 has 12, we can see hopefully that we're going up by 6 each time. So this is the next one, sample 3. I don't even need to count it. This one over here is going to have 8. Is going to have 18. And we're going to go up by 6 again if there was a sample 4, so it would have 24, and the next one would have 30. Okay, so we've filled in the number of cells. The next thing we want to do is we want to fill in the number of edges. So let's see if we can work that out. It's actually not that easy to count all of these, and you definitely don't want to do it for sample 2. So I'll do it for sample 1. See if you can beat me to it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, 24, 25, 26, 27. So you can see that for sample 1, we've got 27 edges. Okay, I'm not even going to count sample 2 because we can sort of see the pattern recognition going on. I encourage you to pause and have a think about how many edges there are. It's actually not that easy. Certainly not easy to count them. We can see, firstly, maybe in purple, and maybe I can highlight it again. We can see all the purple in this sample. This is just sample 1, and we know that all of that, including all the insides, right? Including all these, from before, is equal to 27. Okay, you can probably see that would also be adding on 27 over here, right? If we're adding on sample 1 to itself, we're adding another 27 edges. However, you'd also agree, hopefully, that some of these edges repeat. So along here, and I need a bit of color, along here, right, 3 of these edges count twice. So we're not really adding on 27 new edges. The number of edges we're actually adding on is 24. So what we can do is we can say that this number here, the number of edges for sample 2, is actually going to be 27 plus 24. 27 plus 20 is 47. Plus 4 is 51. So that's 51. We added on 24. Okay, so we're going to have to add on 24 again to get to sample 3 number of edges. So that's going to be 75. 75 plus 24 is 99. and 99 plus 24 is 123. So what we have now is a nice table of values, and in some sense this is everything Duncan wanted to know about it, right? But what would be good is if we could come up with some formulas that actually relate these things together, and that's what the core of linear relations is all about. So let's see if we can do that. So the first thing we might want to do is relate the sample number to the number of cells. So let's have a look at this example. We can see for sample 1, we have 6 cells. So let's just be clear what we've got here. We're in quadrant 1 of our Cartesian plane. On the x-axis, we're going to put the sample number, and on the y-axis, we're going to put the number of cells. So this first coordinate here, we can see we've got 1 as our sample number, and that corresponds to 6. That corresponds to 6 cells, which was just our first diagram, right? So what we can do is we can actually animate this, and we can put this line in, because we know for sample number 2 that there is 12 cells. And we put that line in, and what we can see is it's a nice straight line. And what that means is it's a linear relationship. That's part of what it means to be linear. It goes in a straight line if we're to draw it on our Cartesian plane. So one thing you might notice is that it actually goes to the origin here at 0, 0. And when it does that, we call this directly proportional. Okay, because the number of cells varies directly with the sample number. And see if you can work out the relationship. You probably already have, hopefully. If we look at sample 1, and then it has 6 cells. Well, how do you get from 1 to 6? Well, hopefully you realize we can just multiply by 6. Let's see if that pattern holds. 2 to 12, multiply by 6. 3 to 18, multiply by 6. Seems to work, right? So what we can say is the following. Maybe we can write it as a formula. So let's write down the formula, or the rule. Our rule will be the cells, the number of cells is equal to 6 multiplied by our sample number. Okay, and there's a few ways we can see that. One of the key ways is as follows. You'll notice that as our sample number goes up by 1, our cell number goes up by 6. So we're just adding 6. Now you might be thinking to yourself, right, well, we're adding 6 each time. How come this is 6 multiplied by the sample number? Well, one way I like to think about it is that multiplication is just repeated addition. So we're continually adding 6, or a shorthand way of saying that is we take 6, multiply by the sample number. And you can clearly see that that works out. Excuse me. Okay, one other way we can think about it is as follows, is what's called the gradient. So basically, how steep is this line? You might have heard that word before, is the gradient. And the way we work that out is we basically need to work out the ratio of the rise, so how much we go up, and we need to divide that by how much we run across. So let's just do that quickly. Let's work out how much we rise up. So remember, we're going along the y-axis. So we're saying, all right, how much do we go up? Well, we go from 6 all the way up to 12. So that's rising by 6. And we go from 1 to 2. So that's running by, from 1 to 2 is 1. I'll choose a better color. So our gradient equals, and I take my word for it for now, is equal to the rise over the run. Basically a measure of how steep is that line. In this case, we've got 6 divided by 1. 6 divided by 1. Well, if I've got 6 pens and I share it with one person, how many does everyone get? Well, that one person gets all of them. So the answer to that is 6, which is the same as what we got before. So 6 is our gradient, and it's directly proportional. Okay, so we're done. We don't need to add anything or subtract anything because it varies directly with this. In this case, the number of cells varies directly with the sample number. Okay, the next part gets a little bit trickier. Let's have a look. So a if we wanted to relate the number of cells and the number of edges, it might be a little bit more tricky, but not too bad. Let's have a think. We can see just from a few slides earlier that when we have 6 cells, that meant we had 27 edges. Okay, when we had 12 cells, we had 51 edges. So that's actually just this diagram here. This was sample 2. Sample 2, it's got 12 cells and it's got 51 edges. Okay. Let's use some of our thinking from before and see if we can come up with a rule, and then we can check if it checks out. Let's see how much we go up by each time. It seems to me, and we spoke about this before, that it's going up by 24 each time. 24 going up by 24, 24, 24. So it's actually no surprise that that's going to be part of our rule. So let's see if we can draw this line in. So just to be clear, along this axis now we've got number of cells. Along this axis we've got number of edges. So let's draw that in. Okay. So you can see all those points line up. It's a nice linear relationship. And what we'd like to know is we'd like to know the relationship between them, right? So we know it might have something to do with this 24, but let's use the trick we used before. We want to know the rise over the run. So the rise is how much we go up. Well, we go from 27 to 51. 27 to 51 up the y-axis, or in this case the number of edges goes from 27 to 51, so that goes up by 4. So the run, 6 to 12, that's a run of 6. Okay, so the gradient equals the rise over the run. Okay, so we go up by 24. As we go up by 24, what's interesting is our number of cells didn't go up by 1. It actually went up by 6. So 24 divided by 6 is actually 4. Okay, so we might say to ourselves, okay, this is the rule then. The number of cells, the number of edges equals 4 multiplied by the number of cells. Okay, but let's see if that works. Let's just check and do a common sense check. If I take 6 and multiply by 4, I don't get 27, I get 24. So you can see that I actually need to add on 3. Okay, because 6 times 4 is 24, but then I have to add on 3. Now you might be wondering, why do I have to add on 3? Well, think about what we said earlier. When we said we're actually only adding on 24 each time, right? We're adding on 24 edges each time. So if you think about it, if we had 0 cells, we would actually have 3 edges. Now that might sound a bit odd, but these 3 here are sort of fixed from the start. They can't change. So that's why you sort of get a head start. And this is what's called, when you have that sort of head start, this is what's called partially proportional. Partially proportional. Okay, and then if we look down here, we can actually see, yep, when we've got the number of cells is 0, we've actually got 3 edges. That's because we sort of have those 3 edges that are fixed, and then we just keep adding on 24, but we're starting at 3. Okay, so that one can be a little bit more tricky. But having said that, we do have our rule. What we need to add is we just need to add 3. So this is our rule now. The number of edges, oops, let's use a different color. The number of edges is equal to 4 times the number of cells plus 3. And we said that that's partially proportional because we're having to make that adjustment, that plus 3. So that makes it partially proportional. Okay, let's have a look at the next one. Okay, the last thing that the apiarist wanted to know was the relationship between the sample number and the number of edges. Okay, using some of the skills we spoke about just previously, we can hopefully see straight away that this doesn't go through 0, 0, goes through 0, 3, which means, hopefully we're aware now that that means it's partially proportional. Partially proportional, okay, because it doesn't go through the origin. Okay, so let's draw the line in, let's see what it looks like. Okay, nice linear line again, plotting all those points. Okay, let's see if we can work out the rule. So remember, we said we want to know the gradient would be nice. So let's work out this gradient. How much do we go up, and how much we go across? That's basically going to tell us the steepness of the line. So the rise is equal from 24 to 51. Well, we've said that a few times now is 24. The run this time is from 1 to 2, which is actually just a run of 1. That should make sense. The sample number, as we can see in the table of values, it's just going up by 1. Plus 1, plus 1, plus 1, plus 1. Okay? So as the sample number goes up by 1, the number of edges is actually going up by 24. 24, 24, 24. Okay. So what we can say is we can start to make our rule, hopefully. So the number of edges, let's write it down, number of edges is going to be equal to, all right, the gradient. Well, we said the gradient is the rise divided by the run. Let's write that down. Rise divided by run is equal to 24 on 1, which is just 24. Okay, so it's going to be 24 multiplied by the sample number. Okay, do we need to make an adjustment? Well, let's have a look. Let's have a look at our graph. We can see that when x is 0, y is actually 3. So we do, it's the same as before. And think about it again. We can say if there was a sample number of 0, that would actually have 3 edges to begin with. If we just follow the pattern backwards, right? Follow the pattern backwards. One extra step, we can see that if we had a sample number of 0, it would actually have 3 edges. So we have to add on that 3, again in this case. So we know now that that is partially proportional. So let's highlight that. The number of edges is equal to 24 times the sample number plus 3. It's a bit odd that I've written it sort of down the page, but hopefully you get the idea. And let me just separate some information here. Okay, so that's partially proportional. Okay, so hopefully that clarified directly proportional and partially proportional problems. Here is a few questions for you to try out, and I'll put the answers in the comments so you can practice. And hopefully that clarified some things around direct proportion and partially proportional linear relationships.